Integration by parts is often taught as a standalone formula, but its logic is rooted in the product rule for derivatives. To integrate a product that doesn't fit standard rules, we are essentially running that differentiation process in reverse. This diagram represents a rectangle with side lengths u and v. When those sides increase by infinitely small amounts, du and dv, the change in area is defined by the sum of these new slivers. Integrating those tiny changes gives us the master relationship. The integral of u dv is equal to the total area, uv, minus the integral of v du. Success with this formula depends entirely on how you assign your variables. The LIAT hierarchy, logs, inverse trig, algebraic, trig, exponential, acts as a priority list for u. In a problem like x cosine x, x is algebraic and sits higher on the list than the trigonometric cosine x, so x becomes u. Choosing u based on its position in this hierarchy ensures that the derivative du is simpler than the original term. If these roles were reversed, the resulting integral would become more complex than the one we started with, stalling the calculation. While the standard formula is efficient for simple products, it becomes unwieldy when dealing with high-order polynomials, like x cubed sine x. Solving this manually requires nesting the entire formula inside itself 3 times, which frequently leads to sign errors within the expanding brackets. The tabular, or DI method, organizes these recursive steps into a 3-column matrix. We assign u to the derivative column and dv to the integral column, while the first column tracks the alternating signs required by the formula. We differentiate x cubed until it terminates at 0, and integrate sine x an equal number of times. The solution is the sum of diagonal products. The alternating signs in the first column must be carefully combined with any negative results from the integration column to ensure the final algebraic expression is accurate. By treating the integration as a systematic grid, we can handle polynomials of any degree without losing track of the alternating sign changes that define the master formula. However, the tabular method is not a universal solution. Certain functions, like the natural log in the integral x to the 5th natural log of x, cause the algorithm to fail. If we place natural log of x in the derivative column, it never terminates at 0. Instead, it spawns an infinite chain of fractions. Without a 0 to stop the process, the diagonal multiplication could continue forever. We resolve this by stopping the table as soon as a horizontal row forms a simple integrable product. Multiplying 1 over x by x to the 6th over 6 across the first row creates a basic power rule problem. We stop there, multiply horizontally, and place that result back inside an integral to finish the calculation. Recognizing this failure point allows us to use the tabular structure for organization while manually overriding the process when the derivative column fails to terminate. Let's apply this. Pause here and set up the derivative and integral columns for x squared e to the x. Following LIAT, x squared is our algebraic u term, and e to the x is the exponential dv. The derivative column begins with x squared, and the integral column begins with e to the x. Differentiating x squared down to 0 and integrating e to the x gives us a clean diagonal map. Applying the alternating signs results in x squared e to the x minus 2x e to the x plus 2e to the x. Repeating this procedural flow builds the specific muscle memory needed to execute these steps accurately under the time constraints of an exam. Some problems create a circular loop, such as e to the x cosine of x. Here, both terms are at the bottom of the Lie hierarchy, and neither will ever derive to 0. As the derivative column cycles through sine and cosine, and the integral column repeats e to the x, the table descends indefinitely. No matter how many rows we add, we never reach a termination point. We stop the table the moment a horizontal row matches the original problem. By multiplying across that row and keeping it inside an integral, we create an algebraic equation where our original integral, I, appears on both sides. We add the repeating integral to the left side to get 2i, then isolate our answer by dividing the entire equation by 2. This identifies the solution through algebraic manipulation rather than infinite computation. Solving complex integration by parts problems relies on identifying which stop condition applies, hitting 0, finding an integrable horizontal product, or recognizing a repeating loop. Combining the Lie hierarchy with these three conditions provides a consistent framework for even the most difficult circular integrals.